right, so today we're going to go over the first test review that I gave you for our Unit 1A test. I wish that I could be here with you today, but I'm making this video in hopes that you can fast forward, rewind, rewatch, and use it however best benefits you. This first section is a group of true or false statements. Haha, just kidding. They're all false. And so since they are all false, you are supposed to read the statement, decide which part of the statement is false, and then rewrite the statement with a true statement instead. So in number 1, if a function is increasing on an interval, then within that interval, if a is less than b, then f of a is greater than f of b. So we know it's false. Which part is false? If you said, then f of a is greater than f of b, you are correct. If it is increasing, then both parts should be doing the same exact thing. So let's rewrite it. So here we go. We have, if a function is increasing on an interval, then within that interval, if a is less than b, then f of a, excuse me, I wrote it the same way, is less than f of b. All right. Number 2, an inflection point on a graph occurs where a function changes from increasing to decreasing. So there's actually 2 ways that you could have rewritten this. You could have chosen to change the word inflection point. If you think about what actually occurs when a function changes from increasing to decreasing, you should have said that it would be one of our extrema. Most specifically, it would be a maximum. So a maximum point on a graph occurs where a function changes from increasing to decreasing. That's one way you could have done it. The second way you could have done it is to keep it as an inflection point and instead focus on changing, increasing, and decreasing. Inflection points occur where a function changes from concave up to concave down, or concave down to concave up. The next statement says, if the change in the rates of change of a function is constant, then the function is linear. Now we do know if the rate of change is constant, the function is linear. So you could rewrite it like that. Or you could focus on this first part. If the change in the rates of change of a function. That means that it's a second difference. Therefore, the function is quadratic. All right, so let's look at this next one. For a quadratic function, the rate of change is constant. Well, I actually gave you the answer in the one before. The rate of change is constant for a linear function. So let's rewrite that. All right, now number 5. A fifth-order polynomial can have an absolute maximum. Well, odd polynomials, odd-ordered polynomials, are going to behave like lines, which means that their end behavior will be in opposite directions. They're never going to have an absolute maximum. So we could just say a fifth-order polynomial cannot have an absolute maximum. Now on this last one, a fourth-order polynomial never has an absolute maximum. That is not true. Even polynomials have the same end behavior, meaning that they will definitely have either an absolute maximum or an absolute minimum. So instead of the word never, we could just simply say a fourth-order polynomial can have an absolute maximum. Now I do want to point out, I used the word can because that implies possibilities. It's not that it always has an absolute maximum, but it's possible that it does. Number 7, 8, and 9, we're going to be referring to the graph that is above. I'm sorry, and 10 down there at the bottom. So in this graph, some of the points are marked with letters, and some of them we can clearly see because they cross at obvious points on the graph. Some of them we may have to use approximations. In number 7, they want us to identify the coordinates of any inflection points. So let's review. An inflection point occurs when the graph changes from concave up to concave down, or vice versa. So if I'm looking at my graph, I'll just highlight, this section would be concave down, and you can see that I'm changing to concave up here, and then I change to concave down here, and it doesn't change again. So my inflection points that I'm going to look at are going to be where you see the point C, and it looks like approximately 0, 0. So I would say the coordinates, that includes both your x and y, would be 0, 0 would be a point of inflection, and the other point of inflection would be at 4, 0. Identify the zeros of f and approximate if necessary. So a 0 occurs when the graph crosses the x-axis. This one is obvious. I have a 0 at x equals 0. This one is also obvious at 4. But this last one, I'm going to have to use an approximation. So we'll say 7.7-ish. Number 9, identify an interval where the graph of f is decreasing and concave up. So we just talked about concave up and concave down. What does it mean for the graph of f to be decreasing? In this case, you're focusing on your y values. Where are the y values decreasing? So I see a decrease that occurs. In fact, I'll highlight these sections for you as well so you can see this. I see a decrease in my y values occurring here. And I see a decrease occurring here. I'm supposed to also identify where it is concave up. Well, the only section where it is concave up and decreasing would be from here to here, because this concave up section in the center works. So as far as an interval, I'm going to focus on those x values. That would be 0 and 2. I am not going to use brackets on these intervals of increase and decrease. I simply use parentheses. So from x equals 0, comma, to x equals 2, it is decreasing and concave up. Number 10, for which of the 4 labeled points on the graph is the rate of change of f the least? And how do you know? All right, so what you got to think about is what they're talking about. A rate of change is your slope. And your slope could be positive, it could be 0, and it could be negative. So now let's think about a number line. Where do you find your numbers that are the least? Well, the positives are greater than 0, and 0 is greater than the negative numbers. So I need to look for a negative slope, and I want to look for the slope that appears to be the most negative. So at A, I do look like I have a decreasing slope at A. B, my slope would be 0. C, I would have a positive slope. D would also be negative. So really, I just need to compare point A to point D. Which one would be the most negative? D. Now let's come over to our second graph, and we'll answer the questions 11 through 14. How many relative extrema are found on the graph of G? Now I do want to clarify this. According to the College Board, and the way that they are going to test you on this AP exam, they count every max, min, or endpoint as a relative or local extrema. And then out of those, they choose the absolutes. So if we are counting the relative extrema on this graph, we want to count our endpoints, and we want to count every maximum or minimum that we see. Now notice, I did not put a point around x equals 6 to 7 because that is a point of inflection, but it is neither a max or a min. So I have a total of 4 local or relative extrema. Number 12, how many inflection points are found on the graph of G? Remember, your inflection points occur in between your maximums and your minimums. It's where we change from concave up to concave down. So I'm going to have, I have a maximum at x equals 2 and a minimum at x equals 4. So I will have an inflection point in between those. I also know that an inflection point occurs when I have a change from concave up to concave down here as well. And in between these two, I'm changing from concave up here to concave down here, so I'm going to have an inflection point here. So I have 1, 2, 3 inflection points. Number 13, are there any intervals where the rate of change of G is negative and decreasing? All right, so we want a negative slope, and we also want it to be decreasing. Here's what you need to consider. If the rate of change is decreasing, it means that the graph is concave down. If the rate of change is increasing, then the graph is concave up. So I am looking for a negative slope on a section of the graph that is concave down. That is going to occur between x equals 2 and x equals 3 if I approximate this as my inflection point. So this section is concave down, and this interval from 2 to 3 has a negative slope. We're going to use parentheses to indicate this interval. All right, the final question says, what are the absolute minimum and maximum values of G? So remember, your absolute minimum and maximum are focusing on the y values when x is a certain number. So we have an absolute minimum. And remember, you can use endpoints. We can't use arrows, but since these are definite endpoints, we can use these as well. So we have an absolute maximum that occurs at y equals negative 4 when x equals 8. We have an absolute minimum, which occurs when y equals negative 1 at x equals 4. All right, number 15. I've gone ahead and put the answer here so we can talk about it. Key things that you need to make sure that you have done on a problem like this is, drawn your graph correctly, labeled your x and y axis with the appropriate labels, and then make sure that you have sketched your graph following the labels that you have designated. So Miss Weaver starts each day about 15 miles from Nolensville High School. So we're going to assume in this graph that Nolensville is our destination, and therefore that would be mile 0. So when you start this graph at 15, you're talking about 15 miles away from school, hence the label, distance from school in miles. One day, she leaves home at 6:30 to come to school. After driving at a constant speed, which indicates this is a linear function, for 5 minutes, having gone about 3 miles, she realizes she's forgotten her coffee and heads back home. The return trip also takes 5 minutes. So in both of those, you can see we have a linear function. And I'll just kind of go over this part of the graph. So again, starting at, actually I'll use my arrow. So starting here at, well, excuse me, starting here at the 15, we will travel linearly for 3 miles. So from here to here. And then we stop, go back home for those 3 miles, and then it says she's not able to leave for another 5 minutes, which means she's remaining at home for 5 minutes. That would be constant. Then, because she's running late, she takes a faster route to school than before and arrives after an additional 20 minutes of driving. So since I'm currently at 15 minutes, I add 20 minutes knowing that I need to connect where I am to zero, ground zero, which is Knowlesville High School, creating my final linear function. All right. So now let's go on and look at number 16. Identify the multiplicity of each zero of C of x and explain how you know this. So when you're looking at this graph, first we know it's cubic, which means it will have 3 zeros, 3 solutions. I have 2 of them that are indicated at -1 and at +1. So that doesn't add up, which tells me one of these must appear twice. It must have a multiplicity of 2. So here's what you want to focus on. The fact that on each side of the 1, my output value is positive, it remains the same, tells me that it doesn't dip below that graph. Again, if it works best for you to kind of sketch out an idea of what this looks like, you know that we're going to cross at -1, and you know we're going to cross at +1. And so what you can do is talk about, like, where am I? So at -2, I'm in the negative region, and then I cross, and now I'm in the positive, I touch, and I remain in the positive. So that might help you with identifying your multiplicity, but you can do it on that table alone. So I would write down that x is equal to -1 multiplicity of 1. And I will say again, sometimes they don't write multiplicity of 1. I've noticed in some of the curriculum they're doing it. Sometimes they just don't write it at all, and they only write if there's a multiplicity of 2 or more. So at x equals +1, there is a multiplicity of 2. C of x has a relative minimum and a relative maximum within the interval -2 to +2, but only one of these can be determined exactly. Which one and why? So again, you can kind of look at my sketch, which might help you with this answer a little bit. If we're looking on the interval of these values that were given to us, the only one that we know with certainty is the +1. We know that the graph bounces at that point. It does not dip any lower. So with certainty, we can say that there is a relative minimum at +1. And again, that is because the output values on each side of that point are both positive, which indicates it does not go below. All right, so number 18. We're given a table of values for the polynomial p of x. The polynomial p of x is shown in the table above. What is the degree of polynomial p? Give your reason for your answer. I would advise that you do your differences. I'll take a second and I'm going to write down my answers. All right, so after I completed my differences, which, let me remind you, you can only find your differences if your x values are equally spaced. But after I completed my differences, I noticed that the first difference was not the same, so it was not linear. The second difference was not the same, so it was not quadratic. But the third difference was indeed equal, which means it does have a degree of 3, and therefore it is cubic. So now let's talk about 19. Again, we are given a table of values for a function v of t representing a car's velocity in meters per second after accelerating from a stop. The time t is measured in seconds. Now I'm actually going to write these labels down because this is going to come in handy toward the end when we have to write our answer and label it. So v of t represents meters per second. And t represents seconds. Nineteen asks, is the graph of v of t increasing or decreasing? So what you should be focusing on to determine if it is increasing or decreasing are your output values, which are your y values. And you can see that your output values are indeed increasing. Is the graph of v of t concave up or concave down? Now we want to think about our slope. Remember, if we have an increasing slope, then the graph is concave up. If we have a decreasing slope, then the graph is concave down. In this particular case, our rate of change is increasing, and therefore, this graph is concave up. Can v of t be modeled with a linear function? Well, the only way we can figure that out is to do our first differences. And since our input values are equally spaced, that's pretty easy to do. If I do a subtraction on my output values, I will get the following numbers. So you can see, no, the first differences are not constant. But I can look at those and I already can tell that they are all 2 apart. So, can v of t be modeled with a quadratic function? Yes. The second differences are constant. Number 23. Use the data in the table to approximate the velocity of the car at time t equals 2.5. Since they do specify that this is an approximation, and I would say that 2.5 lands in the middle of 2 and 3, I could just use average in order to find my approximate v of t. So I will take 8 plus 15, and I will divide it by 2. In 24, they ask us to use the data in the table to approximate the rate of change of the velocity of the car at time t equals 2.5. We're also to include the units of measure. Again, since I don't actually have t equals 2.5, I'm going to have to use the two closest points in order to do this approximation. So, how do I set this up? I'm going to do the velocity at 3 minus the velocity at 2 divided by 3 minus 2. This is the closest interval that I actually know values for. So the velocity at 3, if I look up here, is going to be 15, and the velocity at 2 is 8. Three minus 2 is 1. So when I simplify this, I get 7. Now they've asked me to include the units of measure. Since I am doing average rate of change, I need to make sure that I am doing the output per the input. So my unit of measure should be meters per second per second. All right, we've made it to the last page. 25. Identify the leading coefficient and degree of the polynomial g of x equals, and then we have our polynomial. You can expand the entire polynomial and rewrite it in standard form, and you would be able to identify your lead coefficient and your degree. But there is a little bit easier way to do this. Instead of multiplying the entire polynomial out, let's focus on the x terms only. So I have a negative x at the front. I have this 2x that is at the front of this binomial. And I have this x, which is, again, at the front of its binomial. These are all my lead terms of each individual part. I do have to pay attention to the fact that this middle one is raised to the second power. So when I multiply it out, I'm going to take negative x, I'll multiply it times 2x twice, and then I'll multiply that times x. And when I do that, it actually will give me the lead term in my polynomial g of x. So my lead term is going to be negative 4x to the fourth. Now that I have this, I know what my leading coefficient is. My leading coefficient is negative 4. And I know the degree of my polynomial, which is 4. Number 26. A polynomial is fifth order with a negative lead coefficient. State its end behaviors using limit notation. Well, fifth order tells me that it is odd degree, and odd degree polynomials have the same end behavior as a linear function. So the fact that it has a negative lead coefficient tells me it's the same as a linear function that decreases. So I can sketch that out and then describe. We'll start with the left side. The limit as x decreases without bound, and we're just going to make this polynomial f of x, is equal to positive infinity. Now let's describe the right-hand side. The limit as x increases without bound of f of x is equal to negative infinity. So this last section of the review focuses on free response questions. You should always take time to read the directions on these free response questions in detail and make note of any specific things that they tell you about your answer. 27. Calculate the average rate of change of the function for the interval 1 to 2. In order to do this, we're going to set up our difference quotient. I'm going to do f of 2 minus f of 1 divided by 2 minus 1. I will input these values into my function. So when I put 2 into my function, I get 8 minus 2, which is 6. And when I put a 1 into my function, I get 1 minus 2, which is negative 1. 2 minus 1 is 1. Once I simplify things, 6 plus 1 is 7, and 7 divided by 1 is also 7. Number 28. A function f has an average rate of change of 7 for the interval 0 to 6. If f of 0 is 3, what is f of 6? Well, let's just use the same difference quotient that we used above. We'll fill in everything that we do know and then solve for what we don't know. So if I do f of 6 minus f of 0 divided by 6 minus 0, and I set it equal to 7, now I can fill in the parts that I know. Well, I don't know f of 6. That's what I'm solving for. I do know f of 0. F of 0 is 3. I can go ahead and simplify the denominator, and I get 6. And now I have a problem that I can solve. Let's start by multiplying 6 times 7. That gives me f of 6 minus 3 equals 42. And then finally, I will add 3 to both sides. So now I know that f of 6 is equal to 45. So there are a couple ways that I could go about solving number 29. But I'm going to continue to use the difference quotient just because I think that it is good practice for all of us. A linear function f has an average rate of change of 3 for the interval 1 to 5, and f of 5 is equal to 10. What is the value of f of 7? So let's start by filling in the things that we know. Let's do a difference quotient between f of 7 and f of 5. So if I find the average rate of change from f of 7 to f of 5, my problem will look like this. Now, one thing that I do know is because they told me that it was linear, when they tell me that the average rate of change for any interval on that linear function is 3, it doesn't matter if I move around. So whether I'm going from 1 to 5, or I'm going from 5 to 7, that average rate of change is going to be the same. So I can set this equal to 3. Now I'll fill in the things that I know. I don't know f of 7, but I do know that f of 5 is 10. And I can reduce the denominator, get 2, and then I'll solve. 2 times 3 is 6, so now I have f of 7 minus 10 equals 6. And then I'll add 10 to both sides, so I know f of 7 is equal to 16. All right, B. What is the average rate of change of f in the interval 7 to 8? So this goes back to what I said before. If we are on the same exact linear function, the average rate of change is going to be identical for any interval that I pick out. So the average rate of change is 3. Now let's look at 30. Find the x values for which f of x is equal to 0. This is just another way for them to ask you for the zeros of the function. Since this particular function is already factored, they've made it easy for us. We just need to take each factor, set it equal to 0, and solve. So, my first is going to be x equals 0. My second will be x equals -1. And the third is going to be x equals 3/2. And B, find the x values for which the graph is greater than 0. The y values are greater than 0. So again, there's a couple ways that you could do this. You might want to sketch it out. That's perfectly fine. Things that I know about this, it has a degree of 4. If I count up my exponents, I have 2, 1, and 1, which tells me I have a degree of 4. So that's an even degree. Both ends of this graph are going to do exactly the same thing. I also know exactly where this graph is going to cross. It's going to cross at -1. It's going to cross or touch at 0, and then also at 3/2. So the fact that it is even and it has a negative lead coefficient tells me where both of the ends are going to be. They're both going to be going down to -infinity. So here's something you have to think about. Since x equals 0 has a degree of 2, that tells me that it bounces at that point. Another way that you could say that is you could say the graph is tangent at x equals 0. So the way I'm going to sketch this looks like this. So if I am supposed to find the x values for which the y values are greater than 0, the outputs of this graph are greater than 0 when they are positive, which would be above the above the x-axis. So that occurs between -1 and positive 3/2. All right, 31. A function h is a polynomial of degree 5 and has the following zeros: 0, 1, and 1 minus 2i. So the first thing I definitely want to point out to you is to remember that anytime they give you an imaginary number or a radical, they always come in pairs. So even though they did not list it, we automatically know that we have another 0, and it is 1 plus 2i. Now here's the other thing you need to pay attention to. The fact that they said it was a degree of 5. If I look at what I've got written down, right now I only have 4 zeros. So that tells me that either the 0 or the 1 is going to have a multiplicity of 2. So that's why this particular problem says there is more than one possible answer. So when you write this out, you could either write it, let's see, we could have x minus 1, x minus 1 minus 2i, and x minus 1 plus 2i. And I could make the x squared, and that would be correct. Option number 2, instead of making the x squared, you could make the x minus 1 squared, and that would be correct as well. Since we are simply writing down a possible, then there are more than one possible answer to consider. All right, so I think that wraps it up. And like I said before, feel free, rewind, fast forward, use this as it best benefits you.